Hello, everybody, and welcome to a new semester in physical chemistry. Specifically, this is going to be my course on thermodynamics. So, this lecture is mostly supposed to give everyone kind of an overview of, first of all, what is physical chemistry and what are we trying to do. So, at its heart, physical chemistry is the way we try and understand the world. Now, as you can see from the meme, often this means a way we can try and understand the world by applying a whole bunch of equations to it. So that's going to be a very common theme throughout the entirety of this semester. So before we dive into the actual material, I want to take a quick moment on what we're actually looking at. So, good place to start is Richard Feynman, who is one of the more famous physicists of the 20th century, asked, if all scientific knowledge were to be destroyed and only one sentence was passed on to the next generation, what statement would contain the most information in the fewest words? So this is kind of the what's the most important sentence you can leave to the future. So the one sentence that you could that they could use to rebuild all of the scientific and philosophical and underpinnings of our society. Well, his proposed answer actually says a lot about how we can build, uh, how our world is built. And his proposed answer is that all things are made of atoms, which are little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon each other when being squeezed into one another. And this actually says a lot because if you're going to take one piece of knowledge to pass on, pretty much his answer is chemistry. This single statement embodies physical chemistry. And throughout both this course and quantum mechanics, we can actually derive almost all of our chemical findings and phenomena from this simple idea. So let's go ahead and start by really walking through this. So a lot of the actual atomic motion is going to be embodied in um, the quantum mechanics course. This course, we're really going to see what happens when we apply these pieces of knowledge. So, one of these most important principles is to acknowledge that all of our molecules that we saw in general chemistry, they're in constant motion. They never sit still. So, how can these molecules move? So, one of the easiest ways for them to move is to move in the three cardinal directions. So you can imagine if I've got my little CO2 molecule, it can move up, down, left, right, and towards us and away from us. And in these three motions, it's going to be translating. So moving through our cardinal directions. And this is going to embody the movement of the molecule as a whole. We can do the same thing for something like formaldehyde. So again, it can go ahead and go hurtling through space. And we're going to be dealing with a lot of this in the first two semesters, or in the first chapter. However, if I've got a linear molecule like CO2, it can also rotate. So it can also imagine it rotating end over end, or it can kind of like spin. Well, you'll notice the spin won't really do much, and so most of the motion we're actually going to see is this end over end rotating. But these linear molecules have 3 degrees of translation and 2 degrees of rotation. And this is going to become important later. Now, if I've got a non-linear molecule, it's got 3 degrees of rotation. So the first of which is we can imagine this hydrogen tumbling end over end as our little formaldehyde does cartwheels. We can also imagine this oxygen coming over and spinning. So it's going to be moving in this XY. But you can also imagine this carbon oxygen staying still and these hydrogens kind of spinning around that bond. So again, this gets us 3 degrees of motion where we only have two in a linear molecule. And this will actually come into importance later this semester. But what we see is that we have all of this constant movement in these 5 or 6 dimensions is really going to end up influencing a lot of the bulk properties we see in chemical systems, especially in gases. However, it's worth noting that this isn't the only type of motion that a molecule can experience. it can also experience something called vibrational motion. And this is the idea that not only can the molecule move as a whole, either tumbling through space or hurtling through space, but these atoms can move with respect to each other. So, for example, if I'm looking at CO2, we can imagine these oxygen atoms coming closer and further away from the carbon. And as they do this, they can either do this symmetrically at the same time, or they can both move right and both move left. And these are going to be our important molecular vibrations. Now, this is going to be this vibrational motion that is built around the idea that these atoms don't want to get too close to each other because that's going to be repulsive, but they also don't want to get too far away from each other because they're sharing these electrons, which keeps everybody bound together. And it's this push and pull of attraction and repulsion that's going to drive a lot of important chemical phenomena. But for our purposes, we're really going to be looking at this idea of this vibration. And this is again driven by if I'm looking at the distance in between these two atoms, they're going to be at a minimum at some sort of equilibrium distance. They get too far away, and that's unfavorable. If or unfavorable, too close, and that's really unfavorable. So they're just going to kind of swish back and forth in this region. And that's this vibrational motion that we can monitor with things like infrared spectroscopy. Because the problem is that a molecule always has some energy. So it can't go ahead and just stay static at the bottom. It's always going to move. Now, one of the things that we often find is sometimes these atoms aren't well coordinated to each other. So this energy well can be relatively shallow. And that means that as they're moving back and forth, occasionally they'll just go hurtling apart from each other. And this is called dissociation. And this is one of the principal ways we break bonds. So especially when we get into chemical reactions, this idea of giving a molecule enough energy that it can break a bond becomes pretty important. And again, if I do this far enough, this will cause the whole molecule to break apart into separate bits. Now, we can take this idea and now not just looking at a single molecule, but if I have two molecules together, what can happen is I can have a set of reactants and I can go ahead and trade, usually moving one atom from one molecule to another and go to products. However, whenever I have any chemical reaction, there's always going to be some sort of barrier associated with going from reactants to products. And this is going to be the transition state region. And so one of the big things that happens is that as these species get closer and closer, we can often go ahead and get to this transition state where we can jump in from one molecule to another. And this idea of finding the place where we have the lowest energy barrier going from these two species is going to be important when identifying how bond formation or bond cleavage or bond breaking occurs. And if I lower these barriers, this allows us to go ahead and generate a new product species in a chemical reaction. And one of the big things we're going to be doing towards the end of the semester is evaluating the favorability of a reaction. First, by seeing, is it favorable to go to reactants and products? So this is going to be the difference in energy in between this starting and end state. But we also need to look at, is this barrier to go from one to another, is this low enough I can pass through, or is this high enough that even though the reaction is favorable, it will never occur? And so again, this idea of the energy of the reaction versus the energy of the transition state becomes really important. And this is essentially modeled for a single transformation, but you can build this up to full potential surfaces, where you can start with certain molecules and watch as they go through a transition state and then to products. We can use these to evaluate that this reaction is indeed favorable, and we approximately know how hard it is to go through the transition state. Because we know the energy at each state, I can verify how favorable it is to make each of these reaction steps. And so again, this will, if I know the difference in between those reaction products, this gets me how favorable the reaction is to occur. But if I know the energy or how stable the reactants in transition state, I can tell what's the relative probability of going from one state to another. And you need to know both of these pieces of information to figure out if a reaction can actually happen. And we can use this to really describe both equilibrium reactions and rates of reaction. And those are both going to be very important this semester. So this semester, we're going to be working through thermochemistry. So this is specifically going to be looking at how we walk through the movement and energy of molecules and atoms. So we're looking at this movement and using that to describe observable chemical phenomena. So specifically, we're going to start by looking at how we can measure physical properties of gases and how we can use these measured properties to predict other properties of the system. We're also going to spend a lot of time developing a bunch of different models of how energy moves through a system, because again, this will tell us how favorable something is. And this will give us a lot of information about what the chemical system wants to do. Now, the problem is there's no universal model that works perfectly, so we're going to make several different approximations. Some that work good most of the time, and some that are a lot more robust, but much more difficult to work with. Then, once we've developed these models of energy, we're going to extend them to an equilibrium of reactions. So species going back and forth in both gas phases, liquid phases, and solid phases, and then all the way up to full chemical reactions, not just phase transitions. Then we're going to kind of finish up the semester by looking at rates of reaction. So again, not just is products reactant or the reactants favorable or the products favorable, but how quickly can I move in between the two? So if you have not taken it, the other semester of physical chemistry is quantum mechanics. We're going to use some principles from quantum mechanics, but this is mostly going to be the topics of another class. So the quantum mechanics examines essentially the origins of atomic interactions. So it's really looking not at how we go from molecules and atoms to bulk, it's looking at how things happen at the microscopic scale and how these atoms and molecules interact. And this is often going to look a lot at spectroscopy because that's how we examine these molecules. That's how we see what happens, quite literally. Specifically, it spends a lot of time on quantum mechanical properties of electrons and nuclei. This we won't spend quite so much time on this semester, but it also is going to extend how these properties to these translational, rotational, and vibrational motion. And we're going to steal a couple of conclusions from quantum mechanics this semester to build up some of our models, especially at the end of the semester. And then it looks at how we can correlate these electronic, vibrational, rotational, and translational movement into spectroscopic measurements. So more or less, what could I expect to see using instrumentation? And then use these to predict atomic and molecular properties. So we're mostly going to be dealing with this second and fourth point and not really focus on the first or third, as that's really a different course. We're going to steal a couple of these conclusions here and there, and this is where it comes from, and I won't derive them this semester. But if you are interested, please let me know. I'm more than happy to talk about it. So next time, we're going to go ahead and jump full in to looking at the properties of gases. Until then, take care.